So under 2.8 is kind of a different view of the neutron to proton line of stability. And you can then see that if you were in one of these regions, you could be able to predict what type of decay was going to occur, right? We said beta positive electron capture up here, beta minus decay up here, and way out here when you get super heavy, we would predict that the nucleus would possibly eject an entire helium nucleus, which is 2 protons and 2 neutrons. But the cool part is now is section 3, very important, how gammas interact with matter. So, and we're going to go over how all of them interact with matter, but if I have an electrically charged particle, an electron, either positive or negative, the name for this, a positively charged electron emitted from the nucleus, is called a positron. They're both beta particles. We call this a beta minus, and we call this a beta positive. We could call this an electron emitted from the nucleus, and everyone would know what we're talking about. These are not orbital electrons. They interact with matter because they have a charge. They can ionize matter, meaning they can take something and interact with its orbital electrons and ionize matter, whatever this is in the nucleus. They can do something with that electron, giving this a charge, this nucleus in here a charge, right? We already called that an ion pair. Well, anything that can interact electrostatically or electrically can do that. So a proton could do the same thing. A neutron can do the same thing. A gamma. We haven't talked about how a gamma interacts with matter, though, and we know a gamma doesn't have any charge or mass. So a gamma interacts with matter. Here it is. It's just energy. Gamma interacts with matter, and it's kind of like the energy of the sun, you can think of it. And it's a wave of energy coming this way. And my arrows are horrible. And the gamma is going to interact with matter by interacting like this. Here's the nucleus. And I've got orbital electrons. And the gammas are going to strike the orbital electrons. And since they have energy, they're going to ionize it. That's what a gamma can do. It can ionize, and then this ion pair can go on to cause other ionizations, because this immediately gets a +1 charge, and this has a negative charge. There are 3 cases of gammas interacting with matter that we look at, but all 3 of them start out like this. They are called, the first one is called the photoelectric effect. We'll symbol that as PEE, photoelectric effect. And we're all very familiar with the photoelectric effect, right? We know that we've got solar-powered batteries and stuff. The photoelectric effect is occurring. The other one is called Compton scattering, and we'll put that as CS. And the final one is called pair production. You can read about it, but in all 3 cases, whether or not photoelectric effect is occurring, Compton scattering is occurring, or pair production, the gamma interacts with matter by ionizing it by freeing orbital electrons. It is what happens afterwards, whether or not it's photoelectric effect, Compton scattering, or pair production. But all 3 initially make this occur. An orbital electron is freed because of the energy of the gamma. What happens afterwards? Beyond the scope of this class. We can go on, you can go Google these or YouTube these if you want to. But all of them ionize matter by freeing orbital electrons.